सर
हाँ आवाज आ रही है?
जी सर.
आवाज आ रही है. Please.
Sir, should we start, sir, now?
Yeah, we'll start, right? Okay.
Okay, sir. Thank you very much, sir. Sir, actually there was a technical glitch, because of that we are not able to connect.
That's fine. Yeah, this happened. Right?
Okay.
Okay. I'll start, and my screen is visible?
Yes, sir.
Yeah, okay. So again, once again, we move to the second session. This session is very interesting, and because we will talk about the laboratory experiments here. So in this session, we talk about the importance of experiments in earthquake engineering, and we try to show you the behavior of structures under shake table testing. So it will be more interesting, and I think you will enjoy this session. And this part is already covered in the first one, so I'm not going through this part. We say that the earthquake is a man-made disaster, and we have to focus on our buildings. And this is very important. Like in each and every earthquake, we see such kind of pictures, right? Deaths. So these pictures will distract you as a civil engineer. We don't want to see such kind of pictures. We might not be involved directly, but our civil engineering community is involved. So indirectly, we are associated with this. And basically, as a civil engineer, we have to provide a safe habitat. So it's very important for us that we have to provide safe housing or safe structures to all. If you look at the civil engineering profession, then our profession is very unique. Suppose you compare our profession with automobile industry, for example. In automobile industry, if one vehicle is put in the market, before that they go for the thousands of tests, and once they confirm safety and everything, then they put that vehicle in the market. Against that, if we talk about the civil engineering structure, which is our product, we are putting the civil engineering structures without testing. Right? We are testing on materials, everything is fine, individual material. But as a whole, we generally never conduct any test on the structure most of the time. So we are designing our structure on the basis of our assumptions, our theories, and then we put our structures in reality. And you see, you have to feel proud that people are purchasing our houses, our structures, isn't it? They have faith in you. They have faith that as a civil engineer, as a structural engineer, you are going to provide us safe houses, right? And therefore, such kind of incident will happen in case of disasters, in case of earthquake. If we see such kind of pictures, definitely it hurts us. It will distract you, right? So we don't want to see such kind of pictures during earthquakes. And these are the pictures from 2001 earthquake. And you see, we have to avoid the deaths. Number of deaths should be zero, ideally, right? No structure should collapse during earthquake. That is the bottom line. But still, structures are collapsing. There's a reality. We see that these structures are collapsing, and such kind of pictures are quite we have seen during earthquakes. Right? Here, the loss of structural element, like this column is damaged. Right now, still the building survived because we have a lot of redundancy in the system, and therefore the load of this column is transferred to the nearby column, and it might help this structure to stand safe. The health centers, I told you the hospital building in Bhuj was collapsed. These are the schools. Almost 12,000 schools were damaged or collapsed during the Bhuj earthquake. 12,000. Imagine. All of them made up with the prefabricated RCC units. Right? The joints were very weak. This was the reason behind it. Right? The heritage structures are affected. Now, this heritage structure, once it is affected, it is very difficult to restore. Right? So this is a fault. Lifeline structures are affected, bridges or roads. So if such thing is going to happen, it will also create a obstruction in rescue and relief operations. and electric power generally go up. Urban structures, industrial structures are affected, and the economic loss is very difficult to estimate. We know that 54% land of India is vulnerable to earthquakes, 8% to cyclone, and 5% to the flood. And all know that the India is resting on Indo-Australian plate, and Indo-Australian plate is moving below the Eurasian plate. So the formation of Himalaya is because of this interplate interaction, which is known as the convergent boundaries. And you can see the earlier there was a sea instead of Himalaya, and now there is a mountain because of the two plates are coming close to each other. They are interacting. One plate, Indo-Australian plate, is going below Eurasian plate, and therefore this is happening. And this is a seismic zone map of India. This is the epicentral map. This is already we have discussed, so I'm not going to discuss this part. And we said that various little load resisting systems we have, this is a MR frame, this is the bracing system, this is the shear wall, and we have a combination of it, right? You can see this is the beam column system, this is the bracing system. You can see which will effective to transfer lateral loads. This is shear wall system. The shear wall construction is very easy. People before 2001, people are expecting that the shear wall construction is difficult, but it's very easy to incorporate in our structures. And you can see this is the MR frame with the shear walls, right? So generally the moment resisting frame with the shear wall is a good combination, and we have a special resisting systems also. Now we come to the main part. The main part is need of earthquake lab. First of all, why the earthquake lab is required? So we have to discuss many things here. First of all, the earthquake basically it's a random ground motion, but it is a random ground motion, but it's a very strong, right? And basically, the response of your structure to this strong ground motion is also complex, right? And therefore, like we are going for the static and dynamic analysis. We have a code provision IS 1893/2016 for this. We have already discussed earthquake forces are much higher than design forces, and therefore we are following the design philosophy, not earthquake proof, but it is earthquake resistant design philosophy. Earthquake resistant design philosophy means damage is allowed but collapse is not allowed. And after each earthquake, you see there is a refinement in the codal provision. I told you that IS 1893 part 6 is coming, that is related with the base isolation techniques, right? So for the laboratory testing, we need a physical model, we need a earthquake simulation, and these two things are required to understand the behavior of the structures. And the SIG table is one means of the laboratory testing of the model, right? And generally the various tests we are performing, right? Various tests we are performing on the model, right? So we talk about a dynamic test of model. There are free vibration tests. You can see free vibration test. The free vibration test means initial displacement. We actually allow the displacement and then we allow our structure to move. Initial velocity test, we give the impact. Force vibration test means shake table testing, the resonance testing, everything will come under this. So different type of testing we have. Even ambient vibration test is also there. So as far as today's presentation is concerned, I'm not going in detail of this all types of testing, but I will focus on free vibration test as well as resonance test and shake table testing, right? This is we are going to discuss today. Okay, now to perform the dynamic test, basically we require three things. One is the equipment to provide dynamic force. That is the shake table. The shake table is generally used to provide the earthquake motion. So it is known as the earthquake simulator also. Second, we need a model of our structure. So it may be a prototype, maybe a scaled or experimental model. So today we are going to discuss experimental model. And third is when your structure is going to respond to the motion, then we have to catch up. We have to catch up the its deformations, acceleration, all the parameters we have to catch up. So we need the instrumentation setup that is to be required, right? So three things: shake table, models, and instrumentation. Means we require the data acquisition system, vibration analyzers. This is what we need, right? So first we talk about the shake table. So what is shake table? The shake table is a laboratory equipment which is capable of reproducing the motion of the ground during the earthquake. All right. So this shake table will actually we are using as a to impart the earthquake motion. It is basically a 6 degree of freedom. Shake table is the most suitable. Means we want a 6 degree of freedom shake table. It means the shake table is having a shaking in to horizontal direction, vertical direction, as well as rotation in all the three directions. So 6 degrees of freedom is required. Uh, and we are going to test the prototype or scale models in the laboratory, and this shake table helps in investigating both the responses, linear elastic or non-linear inelastic deformation, right? uh, so here we go through the certain shake tables which is available worldwide. If you look at this shake table from University of Berkeley, California, we have, and if you look at the size, 20 feet by 20 feet is the size, and payload capacity is almost 1 lakh pound. It is servo hydraulic actuator controller, and it is having 8 actuators in horizontal direction and 4 actuators in vertical directions. And the maximum acceleration you can impart is 1.5 g. So this is 6 degree of freedom shake table. Right. So it is having the 2 horizontal shaking, 1 vertical component, and 3 rotations. All. This is the shake table from NID Japan. This is world's biggest shake table available, and is having a capacity of 1200 ton. I tell you, we have developed a shake table here in our laboratory, having a capacity of 0.5 ton, 1 ton capacity we have prepared. Now, if you look at the size of the shake table is 20 meter by 15 meter. So you can test the actual model here, actual structure here, right? 20 meter by 15 meter. It's too big. And if you look at the maximum displacement 100 mm in in vertical direction is 50 mm, and the torque maximum allowable moment is actually 150 meganewton meter. That is in an x direction, right? So this is I think state of the art shake table available worldwide. This is one of the biggest and the best shake table of the world. We have a good facility at IIT Kanpur, IIT Roorkee. They have a shake table, and model can be tested. Now this is the video, actually the picture from UC Berkeley, where they are testing 1/5 scale model. You see, 1/5 scale. This is so big. Still, it is 1/5 of a 7-story RC frame building. So testing is definitely become difficult as far as real structure is concerned. That's why I'm saying that people is having trust in us. They are putting faith in us that whatever we are giving without testing to them, they are accepting, and by assuming that we are providing them safe houses, right? So basically 6 degree of freedom shake table is basically difficult, and therefore as far as the rotational component is concerned, the rotational component is important in certain cases. Otherwise, if you neglect the rotational component, then 3 components are remaining: two horizontal component and 1 vertical component, right? And I told you that the vertical component means that there is a shaking in the vertical direction. Now, when the shaking in vertical direction, it results in the increase in the force in the column in the axial direction, right? Now, when we design the column, we are using factor of safety 1.5. So this 1.5 factor of safety means your column is subjected to 100 kilonewton force, but we are designing for 150. It means your column is having a reserve strength of 50 kilonewton, right? So this 50 kilonewton reserve capacity of your column will take care of the vertical component of the earthquake. So vertical component is not important if your structure is located away from the epicenter. So what is the predominant action? Is the horizontal. So remaining is the horizontal direction. This is we require. So we have two components basically. We have two components in x direction and in z direction. We have two components. Now it means we have to develop a shake table which is in both the direction, right? Which will shake your model in both the direction. Instead of that, the code is saying that you test your model in one direction and then test in the other direction. So what exactly, if you have a suppose instead of biaxial shake table, if you have uniaxial shake table, then you test your model in one direction, then change the orientation of your model. You change the orientation of your model and test in the other direction. So we say that 6 degrees of freedom shake table is very costly, and so therefore this uniaxial shake table basically serves the purpose because it is cheap and it gives the behavior of structures under the lateral loading, right? So we test the model in one direction, and then we change the orientation of the model and we test it again, so we get the response in the other direction also. So uniaxial shake table is okay. So these are the various shake tables basically available in the lab. So this is the shake table, is a uniaxial shake table, right? Where the frequency range is 0 to 25 hertz, payload capacity is 500 kilonewton, and the displacement capacity is 260 mm, right? We have a instrumentation setup. This is the vibration analyzer, 16 channel vibration analyzer. 16 channel means you can acquire 16 data at a time. It means if you put a sensor on one floor or one column, you get the acceleration of that particular column. So 16 records you can have at a time, right? You can record through sensors. So we have a uniaxial accelerometer, triaxial. Uniaxial means it gives the acceleration in one direction. Triaxial, it will give the acceleration in all the three directions. So triaxial sensor. So suppose if I'm talking about the 16 channel, it means suppose I am having a 10 uniaxial sensor, means I am getting the 10 records, and I have 2 triaxial, means 6 records. So 16 channel will serve this purpose. Or you can have a 3 triaxial, then 9 response, and remaining is 7. So 7 uniaxial sensors you can use, accelerometer you can use to capture the response of your structure, right? So the first part of the experiment is actually we are preparing a model. We are testing the model on the shake table. So therefore we have to determine the property of the model first, right? So first of all, we have to determine the property of the model. We have to determine the stiffness of the model. We perform the impact hammer test, free vibration test, and the shake table test. So this is what we are going to do as far as the laboratory experiment is concerned. Suppose this is a frame, right? Now this frame is a rigid frame, right? So what we do here, here we are putting the, you can see this is a 2-story model, right? So this is a 2-story model, and what we are doing, we are locking. You see, we are locking one floor, and we apply the force here. We apply force at this level, right? And then we record the deformation. So we get the actual stiffness of the structure, right? So what actually we do? We do like this. Basically, it's a the 2-story structure of 1 and 2-story. So what we do here is we we apply the force on the first story, right? And we get the stiffness of the first story. Then we lock the first story and apply the load on the second story. We get the stiffness of the second story, right? Practically, we get this actual stiffness. This stiffness we calculating in laboratory, on ground. We are measuring this, right? So you get the exact idea what is the stiffness of your model, right? And you can also verify the stiffness with the theoretical calculation also, and you can also have idea that what are the differences in the stiffnesses and why differences is there, right? So that is to be there. So here First is the determination of the stiffness. So whatever model you have, you must know everything about the model first, right? You must know the property of the material as far as model is concerned. You know the stiffness of the model. Everything is needed first, right? So these are the some, and then basically we perform the free vibration test. Free vibration test. What is free vibration test? Basically, free vibration means your structure is there, right? And then we allow the displacement, right? And then we are leaving. Now your structure basically flexible. It possesses certain stiffness, certain flexibility. So suppose if I am stretching the structure and then relieving, then the structure will vibrate. Structure will vibrate. How structure will vibrate? That we'll see this video. Uh, you can say whether it's visible or not. It's,
Yes, sir. The yes,
you can you can see this. Is it visible? Nah?
yes, sir.
Yeah. Now you see this is basically a three-story model, and what you are doing? You are disturbing. You are just stretching it, right? So you are, yeah. So now because your structure is flexible, it will vibrate. Now you can see here. You can see here sensors are here. Sensors are placed at every level. It will capture the acceleration of the slab, right? So we are capturing the response of our structure. Now you can see here what is happening actually. Look at this. Your structure is vibrating. So initially you have the maximum displacement. This displacement is keep on reducing from cycle to cycle, right? In each and every cycle, this response is reducing, right? We are knowing the responses keep on reducing, right? So here, this is the expression in which we are calculating what is the amount of damping present, right? So this is the equation which is given in the book of A.K. Chopra, and we can refer this and to calculate the damping, right? So again, one more time, we will see the video and you get a clear idea what exactly we are doing. It's a free vibration test. Free vibration test means only initial disturbance is there, and later on we are not disturbing the system. This is a sensor. This is on the top. It is a sensor, right? Sensor is placed, and the sensor will measure the acceleration in the direction. So sensors are placed on the shake table on all the floors. So when we disturb the system, so this is we are disturbing the system. We are applying the only displacements. You see, we are applying only displacement and relieving. So it is a free vibration test. What is the free vibration test? Only initial disturbance is there, and then the system will vibrate on its own elastic property, right? And the sensor will catch the acceleration and the frequency. Every parameters will be taken care, and we find out what is the acceleration after the processing. You can see here, if you look at this curve, then this is a curve of displacement versus time. So displacement is keep on reducing with the cycle to cycle because it's a free vibration test, right? So this is the free vibration test we are going to perform. The second is impact hammer test. The impact hammer test means it is the initial velocity test. Initial velocity. You see, this is basically this is a impact hammer. This is the hammer, right? And on the tip here the sensor is there. This is the sensor, right? Now this you can connect with the wire here. You can connect here, right? This wire. So when you apply the impact using this hammer, then the sensor will sense how much energy you have applied. It is recorded by this hammer, and actually we apply this energy to our model, then the model will vibrate. So it is known as an impact hammer test, right? So you can see here, this is a hammer, and here the impact is given here. Here impact is given, right? And You see, this impact is very minor, right? And even though our sensors are sensitive, it will capture all the data, right? And you can see here how we perform the impact hammer test. You can see this. Now this is the simple model, and the impact is given. Now you can see this spring mass system is vibrating. This spring mass system is vibrating, right? So this is actually this data is captured in the software. That this is the impact given, this is the energy given. At the same time, what are the displacements observed, corresponding displacement observed. If you apply more energy, then again I'm repeating this impact hammer test. If you apply more energy, then response will be larger. That's all, right? So here, this way we are performing the impact hammer test. This is known as the initial velocity test. Initial velocity test. Earlier it was initial displacement test. Now it is the initial velocity test. Both are free vibration test. We are only going for the initial displacement, initial velocity. That's all. So only initial disturbance is there. That's why it is known as free vibration test. So difference between the free vibration and forced vibration is, in the free vibration only initial disturbance is there. In the forced vibration, during vibration we are disturbing. We are applying the energy. That is the forced vibration test. So here we are not performing for vibration. This is the free vibration test. Now we go to the third test. Is the shake table test. Now here we are mounting our models on a shake table, and then the shake table will be applied the motion, and then we record what is the response of our structure, right? And we determine the natural frequency of vibration, acceleration, natural period. Everything is determined from the frequency response curve, right? So now we go to the single story building, right? Single story building means, you see, this is a single story building having a single slab. The single slab is having a very heavy mass at one location, right? So if the earthquake force is acting in horizontal direction, in this direction, right, then a heavy mass is located here at this level, this slab level, right? Heavy mass is there because the slab is very heavy. And what is earthquake force? Earthquake force is mass into acceleration. As it is mass into acceleration, it generates a heavy or large force at this particular level, right? So what we are doing, we are knowing that the masses are present here also, but this mass is negligible as compared to the mass of the slab. So we are saying that it is a single story building having a single degree of freedom system. We are saying that this mass is very heavy and this mass is going to vibrate in horizontal direction, right? So we are going for the mathematical model. So what we do here, we can say that the heavy mass is located here, and this mass is connected with the columns, right? These columns. So when we prepare a model, this is the mass which is connected with a spring. Because this column possesses certain stiffness, and you see, once you disturb it, your system will vibrate and it will come back to original position after some time. It means certain amount of energy is dissipated. So this is the damping. It means damping is present in the system, and this is what the mathematical model is, right? So as far as frequency vibration is concerned, it is frequency is 1 upon 2 pi square root of k by m, right? And what is k? For example, if I take 3a by l cube or 12a upon l cube, if I take this 12a upon l cube, then the stiffness depends on what? The stiffness depends on E value. Elasticity depends on I, moment of inertia, it depends on length, right? These three things. Which three things? Again, I'm repeating. What is length? Length is this. When we are saying this is the length I'm talking about. I'm talking about the E and I. E means modulus of elasticity. Modulus of elasticity. It depends on material. Which type of material you are using. I means moment of inertia. What type of cross section you are using, right? So EI and L, and the 12 is giving either 3 or 12a by L cube or 3a by L cube. It depends which type of support condition you are using. If a mass is allowed to rotate, it is 3a by L cube. Mass is not allowed to rotate, it is 12a by L cube. So it depends on the condition. So stiffness depends on EI L cube. right? And the fourth parameter is the mass, right? So the first, you see, basically we have prepared different models to understand the behavior, right? So most basic model is a spring mass model. Spring mass model, right? Spring mass model means we say that this is the slab where the heavy mass is located is a heavy mass. So it is a you can say this is a mass, and it is supported on column. So column is having certain stiffness, right? So we say that uh, this is having certain stiffness, certain mass, right? So which are the parameters we have to consider? The parameters we consider that the value of E will change. So if we use the different material, E will change, because we are knowing that the stiffness depends on, means frequency depends on K and M, and K depends on E, I, and L. So if we vary E, if we vary I or L or mass, we can vary these four parameters, and we try to study one by one that what is going to happen with if we change this parameter, right? So we are changing these parameters. We change the material. So here we are changing the we're talking about the E. What is the effect of E? Then if we change the height, then what is the value? This means L is here changing, and what is the effect on response? Here we are talking about the change in the mass. Here we talk about the thickness. Thickness means we are talking about the value of I, changing the value of I. What is the, you see, you can correlate. Suppose if I'm using, if I'm talking about the masonry structure, the value of E is different. If I'm talking about the RCC structure, value of E is different, right? So which type of structure we are talking about? So E will change accordingly. Height. Suppose if I'm saying that my drawing room is having a double height, and the remaining rooms are having a single height. So if double height is there, then behavior of this double height column is different as compared to the single height column, because your stiffness will change. Mass. Sometimes we are saying that okay, we are putting heavy mass. If we go for the flat slab, we go for the normal slab. Then flat slab is having a higher mass. If you go for the higher mass, then what is the impact on the structure? We have to see. Thickness. So we have a column of 300 by 300 size. We have a column of 300 by 600 size. You see, if the thickness, if the B and D will change of the column, then I will change. So it's the response of the structure may change, right? We have to go to that part. So this is the first part where the material is different. Here you can see the different material you have. Here maybe a cast iron. Here the flexi ply you have, brass and copper you have. This is brass, brass. This is copper you have, right? So then we perform a free vibration test. When we perform a free vibration test, you get the result. When you perform a shake table test, you get the difference, right? So we have to perform all the tests. First, we perform a free vibration test, displacement test. Then we go for the impact hammer test. Then we perform the shake table test. And the most important part, you see, these are the graphs of acceleration versus time. You get this is the acceleration and this is the time, right? This is the graph of acceleration versus time, right? And this is the FFT. This is the acceleration. You see, this is the graph of acceleration versus frequency. This is very important graph, right? We go for the FFT analysis. Now here you can see when we plot, here it is acceleration versus time, while here it is acceleration versus frequency. So you see, our structure is a single Storey structure. It's a only single mass is there. So we get a one frequency. You see, here we get a one peak. We get this graph, but we get a one peak, and this one peak is nothing but this is the frequency of your structure. This is the frequency of your structure, right? So this we can have. So we can have a stainless steel. We have a flexi ply, right? So here we can see the spring mass system. You see what we are doing? We are putting all the four models on a single on a shake table, right? And then we apply the motion. and we see what is going to happen to your model, right? So we are applying the same motion to all the 4 models, right? And how it behaves, you just go through this part, this video. It will tell you the concept of resonance, right? What is the resonance? The resonance is,
Please tell.
yeah. Now here you can see there are basically four spring mass model you have. One is with the steel, another is flexi ply. Now we apply the certain frequency, right? We apply the certain frequency. Now you see all the 4 models are given the same frequency, but one is vibrating more. Now frequency is increased. Now when the frequency is increased, what is happening? You look at the behavior. It will increase. The next model is vibrating, right? It means the frequency of this model is higher than the previous one, and it is vibrating. Then if you are still increasing the frequency, shaking frequency, you see what happens. When we increase the frequency, then now the other 3 are not responding, but the third one is responding. You see, first, second, and fourth is not responding, but third one is responding, right? And it means the frequency of this model is close to the frequency of shaking, all right? So this is the reason of resonance, right? And here the sensors are placed. You see, sensor is on the top. Uniaxial sensor, it is there on the top, and it measures the acceleration. Now still I am increasing the frequency. Just look at this again. If I increase the frequency, what is happening? Now the first 3 are not responding, the last one is responding, right? It means the frequency is close to this particular model. So sometimes the question will arise that which building will be affected during earthquake. So you cannot say which building will be affected. It depends what is the frequency of your structure and what is the frequency carried by the earthquake. This is very important. If I'm saying I'm talking about a structure is having frequency 5 hertz, and if earthquake carries the 5 hertz frequency, those structures will vibrate more, right? But if earthquake carries 10 hertz frequency, then 5 hertz structures will not be affected. So you can only say that your structure will be affected on the basis of the frequency of your structure as well as the frequency of the earthquake shaking. If both will match, then the larger response will be there, right? So here, this is the spring mass model we can have. This is a basic model where you can study the response, right? You see, then what exactly we do? We have mild steel, stainless steel, flexi ply, brass. We have this. So we are using basically this analyzer, vibration analyzer. We calculate the frequency. What is the frequency for the mild steel 3? When we model this in STAD software, then we came 3.181, and theoretically it was 3.4. So you can see these frequencies are close enough, right? This variation may be because of maybe the end condition and everything. If you look at the stainless steel, then if you perform the experiment correctly, you have 1.15. When we model this in STAD, it is 1.5, and this is 1.52 theoretically. I'm knowing what is the mass, what is the stiffness, everything, all the geometric data, all the material data I'm having, I can calculate theoretically also. Right. So you can see, you can compare this, and then you have a proper satisfaction that okay, what I have tested is correct and it matches with the theoretical values, right? Then the next model is a variable height, right? Sometimes we are saying that my column is height of the column is 10 feet, for example. You can say, okay, my height of the column is 12 feet, or height of the column is 15 feet, height of the column is 20 feet, something like this, right? So when we compare the first and last one, right, then there is a difference in the height, double, right? Now, whose stiffness is higher? The stiffness of shorter one is higher. Stiffness of this is higher. What is the reason? Because it is 12 EI upon L cube. If L is the denominator, if the L is less, stiffness is high. So this is basically stiff. This is flexible. This is flexible, right? This is flexible. This is flexible, right? And this is stiff. This part is stiff. Okay. And again, you can have a same thing, analyzer, means result of testing, then stat and theoretical compare. Almost you get the same type of results. Means if we perform correctly, right? Then we have different masses. You can see here. This is the having least mass. Then the collar is attached here. This is the collar. Mass is added here. Then mass is added here, right? So this is the having the maximum mass, while this is having the least mass. So what is the frequency? Frequency is square root of k by m. Now if the this is having least mass, mass is less, so frequency is high, and this is having higher mass, so frequency is less, right? This is you can conclude. Again, the same thing you can perform, right? Spring mass model of variable thickness. Okay, so we can perform the test. Now we go to the next part. Here we are talking about a multi-story building having the three floors, 1, 2, and 3. So there is a 3-story structure, right? It means it is like this. This is the 1 floor, this is the 1st floor, 2nd floor, this is the 3rd floor, right? So 3 floors we have, and again we test on the shake table. So what is going to happen? We are getting when we model it in the software, then we get the different mode shapes, right? Mode shape means for certain lowest frequency we get this type of shape. Then for the higher frequency we get this shape. For the then next higher frequency we get this such shape, right? This is the shapes which is known as a mode shape. You can see here. We will perform the test here, and you see this here we have a lowest frequency. Remember, this is having a lowest frequency. Then the here you have higher frequency, and then here you have highest frequency, right? So you can see here when we perform a test on a shake table, then what is going to happen? You can see it is quite flexible system. We put a sensor here at top, all the 3 level we put the sensor, at the bottom also on the shake table it is placed the sensor, and you can see the mass is, the shape is something different at lower frequency. Now frequency is increased. When the frequency is increased, the shape is changed. So response of your structure depends on which type of shaking frequency the building is subjected to, right? So now you can see response is quite subside, right? Again I'm repeating. Just look at the model again. Here lowest frequency is applied, shaking frequency, and you can see the response. This is quite flexible, so response is very high. Now if I increase the frequency, then what is going to happen? The frequency of structure and frequency of table is not matching, so response is coming down. Response is coming down, right? Again I'm repeating this. You have to understand this. What is resonance? This is having a low frequency. This is a low frequency model, right? So when I'm testing this at the lowest frequency, you have a larger response. It means it comes into resonance, right? And when I increase the frequency, then it crosses the frequency of structure. So now response is reduced, right? So therefore you have to be very careful. Sometimes people are saying that okay, in earthquake a high-rise building will be affected, or low-rise structure will be affected. Now which structure will be affected? Can you tell me? High-rise or low-rise? During earthquake, which type of structure is affected? Anybody?
High-rise.
High-rise is affected. You see, this is the most common answer we are receiving, but you cannot say high-rise is affected. You see, when we're talking about low-rise structures, the frequency is high, and when we're talking about the high-rise structure, the frequency is less, right? When you calculate the frequency of low rise structure, it is always high, and frequency of high rise structure is always low, right? Now, you see, when the low frequency earthquake will come, then the high rise structure will be affected. And when the high frequency earthquake will come, then the low rise building will be affected. You cannot say simply high rise structure will be affected, right? You get my point, what I'm saying? Yes or no?
Yes, sir.
Yeah. So again, the response of your structure depends on what frequency earthquake carries, right? If earthquake carries the frequency what your structure is having, then larger response will be there. So that's why I'm saying that during 2001 Bhuj earthquake, in Ahmedabad, 128 buildings which were ground plus 4 story, they were collapsed, and only 2 buildings ground plus 10 story, they were collapsed. Now question will arise, why this is happening? There are many reasons, quality of construction and many other issues are there, but one of the reason was the frequency of earthquake was little close to ground plus 4 story structure as compared to ground plus 10 story structure. It is not, I'm not saying resonance was there, no, resonance was not there, frequency is continuously changing, but the frequency was little close to the ground plus 4 story structure, right? I'm giving you example of 1984 Mexico City earthquake. 1984 Mexico City earthquake, what happened? A very low frequency earthquake was there, very low frequency earthquake. And in Mexico, like almost 7 to 15 story buildings affected a lot. And when the engineers have analyzed that why this 7 to 15 story affected, because it was very low frequency earthquake, and why these buildings were affected. When they analyzed, they found certain interesting thing. What was that? They find that the frequency, actually it was a very low frequency, but the whole Mexico City, basically it is constructed on a soft soil. Earlier there was a lake, and this lake was filled up. When the lake was filled up, it is a filled up soil, and the frequency means it is a soft soil basically. And then when this low frequency earthquake came, and this filled up soil, it's a soft soil, is having a characteristics that it will magnify the motion, and it has magnified the low frequency to certain frequency, and this frequency matches with the frequency of the 7 to 15 story structure, and therefore this 7 to 15 story structures are affected a lot. If the number of stories less than 7 or more than 14, they are less affected. So this was the observation of Mexico City earthquake, right? So therefore, always when you try to answer the which type of structure will be affected during earthquake, then you have to say it depends on the types of earthquake or which frequency earthquake carries and what is the frequency of our structure. It depends on these two criteria, right? It depends on many other criteria like quality of construction and many other things, right? But the one of the things you can say this, right? So this is the behavior of the multi-story building you have, and you can see here. This is a beautiful thing. Here we are saying that my structure is vibrating in the first mode or second mode or third mode. Here you can see. Here 1, 2, 3 and 4 floors are there. This is the first floor, this is the second floor, this is the third floor, and this is the fourth floor. When all the masses are moving in one direction, it is the first mode, right? If I change the higher frequency, you can see we have captured the another mode. Here what is happening? This mode shape is captured. This mass is moving in this direction, while this mass is moving in opposite direction. Right? This is going to happen when you change the frequency. So you have a different shapes of deformation during the earthquake. This is going to happen. Look at this shape. This shape is something different as compared to this shape. So you can say this is the first mode of vibration. So you have studied what is the generally we are saying that you have to consider in case of multi-story building, you have to consider the mode shape up to 90% mass participation. This we are saying as the code is saying. So this is the first mode. Maybe this is the second mode. Likewise, you have third mode, fourth mode. So this mode analysis can be done in the laboratory, right? So this can be done very easily. And here you can see this is again the experimental result and the stat results. Almost they are matching. It is not the exact one, but they are very close to each other, right? Now, this is some dynamics part we have discussed, but now that we talk about the reality. we are talking about the structures which are collapsing during the earthquake. Now they are maybe a open ground story or soft story structures. Vertical irregularity you have a stiffness irregularities, right? We will see this. Right. What is open ground story? The open ground story means we generally provide a parking at the ground story, right? Parking at the ground story, and the people are start living on the first floor. So what is happening on the ground story? You have only columns, while on the first story you have column plus you have walls. You also have the walls, right? Walls also you have. So which part is stiff? The ground floor is flexible, and the first story is stiff, right? Here again you can see here only the columns are there, but on the first story you have column plus wall, right? So the ground story is flexible, upper story is stiff. Again you can see here, this is generally we are providing such kind of system in India, and this is generally this is a ground story where only columns are there. On the first story you have walls also, right? So the ground story is flexible. Remember, ground story is flexible, upper story is stiff. So the soft story means the story whose stiffness is less than the upper story. It is known as the soft story. In the previous code, it was mentioned that the stiffness of any story is less than 70% of the stiffness of the upper story. It is a soft story. It was defined in the, but now in the new, it was removed. Here again, you can see these are the soft story, right? Now here you have car parking. The space for the car parking is there, right? Here you can see this is a ground story is for the parking only, right? So what is going to happen? Here you can see here the ground story. The ground story is flexible. Its ground story is flexible. Maximum deformation is on the ground story, and upper portion is very stiff. So upper portion moves as a whole, right? So the whole building behaves as an inverted pendulum, right? We can say this mass is as a single mass and it is vibrating on these columns, right? Because it is soft, and you can see what is happening. Here you can see what is happening, right? This is because of this reason. Now here you can see we have 128 buildings, ground plus 4-story collapsed. Out of these 124 buildings, almost 90% buildings collapsed due to this soft story effect because of the parking on the ground story. You can see here these columns are collapsed on the ground story, but the upper part, you see, as such, no damage. Damage is there, but because of collapse of the lower story. You can see here ground floor column collapsed, but the upper part is almost nothing has happened to upper part, right? So we have to pay more attention to such kind of problems, right? You can see here there's a beautiful mountain, and therefore when you are living on the ground story, you feel that okay, I must have a glass window, and I open up, I have a beautiful view. But by doing this, you are making your ground story soft. So this will become soft and upper is stiff. So you see, nature is so powerful. Within 2 minutes of earthquake, he identify all the deficiency, right? This is the wrong practice, right? Again, you can see here, ground story columns are collapsed, and upper part is almost nothing was done, right? So this is known as a soft story failure. This is a soft story failure, right? So the reason is the shear was not present in the ground story. It's a soft story effect, right? So now we will see what is the soft story effect. I think the orientation is something wrong. Orientation is how to make it 90-degree rotation. Anybody is doing?
Sir,
Yes.
because of the mobile, I think the video is taken with the help of mobile, I think, sir.
How to see? Okay. I think this video if you can see, just look at this. You see ground here. Here what is happening? On the ground story there is no wall, and here you can see here wall is there, right? Here wall is there. So it is like a open ground story structure, right? And now what is the behavior? You can see the upper part is moved as a rigid body, and lower part where the deformation is there. All right. I think next video will be more. I'm not able to rotate it right now. That is a problem. Rotation is possible, but I think options are not here right now. Okay, we are not wasting the time in that, but I think that the next video is the soft Storey failure. Now you observe this. This is very important. You see, again, here the walls are there. On the ground story, there is no wall, right? Just look at this. And here the students are also very excited. Look at this. Here you can see the failure also. So this is a soft Storey model. And we are applying the shaking frequency. Now you look at the upper part is more as a rigid body, and the deformation is at the ground story, right? Look at carefully. Look at carefully now. Right, upper part is moving like a rigid body, and in the ground story, what is happening? On the ground story, yes, larger deformation, and this is gone. You can see this is collapsed, right? This is broken, right? So this is the soft Storey failure, and lot of energy. When you touch this part, I think a lot of heat is generated. It is too hot, right? The same thing happening with the other structures also. You see the deformations is observed in the ground story. So my request is that avoid the soft Storey, avoid the parking. If you want to go for it with the proper design considerations, right? So that is to be required. Okay. Again, I think this you have to see it again so you can appreciate the soft Storey, because 90% of building in Bhuj earthquake was collapsed due to this reason, right? And India still we are following this practice without proper design considerations. If the proper design considerations are there, fine, nothing is wrong. You can also design such kind of structures, but you have to pay attention to it. That is required. Look at this, right? Larger deformation on the ground story. Upper story, almost deformation is not there because of stiffness, high stiffness. Now look at the failure. Look at the failure now. Look at the failure. Larger deformation, and it is gone, right? So I think this is sufficient. Okay, so we move ahead with the next part. So here you can see we have calculated the peak acceleration, displacement. Now here the most important part is, look at this. What is the total deformation? The total deformation is 40.7, and out of this 40.7, 29.8 means almost 75% deformation is on the ground story. It's supposed to be distributed along the height, but instead of that, 75% deformation is on the ground story, and therefore the failure is observed, right? This is very important for us. So displacements are very high, and you see our concrete structures, our steel structures having limited deformability. If deforms more than certain limit, it will collapse. We have sometimes the middle story to be soft. Middle story means you can see sometimes what we need a auditorium on the 6th floor. So auditorium. So we remove the column. What happens? Almighty nature has found out the weakness within 2 minutes. 2 minutes, the weakness is found out, and the whole structure came down. Right? You can see here. This is structure is okay here on the ground story is okay here, but it collapses here because the soft story was here. Here only columns were there because they have put certain place for the open space they have provided here, and because it failed, right? So when you go for the asymmetric shear wall, asymmetric means we are providing a shear wall on one side, right? Generally, what is happening when we are when we are, you see, if you are structural engineer, you civil engineer, you know that we have to deal with the architect, and architects are saying that my front part, the front part of the structure should be look good, and therefore you cannot provide shear wall in the front. You can provide the shear wall on the back side, right? So we place the shear wall on the back side. For the normal circumstances, it is fine. But suppose during earthquake, what is happening? You can see here during earthquake, it induces a torsion. Just look at this. One part is stiff, another is flexible. So one part will move more, stiff part will move less, and you can see how your structure is vibrating. Again, a problem of rotation is there. So please excuse me for this. Here again, you can see the rotation means torsion is introduced. It is very difficult to deal with the earthquake forces. And if you add the torsion in this, again I'm repeating, it is very difficult to deal with the earthquake force. And in addition to that, you include the torsion, you make your life miserable, I tell you, right? And torsion is the worst thing as far as earthquake is concerned, right? So you have to be very careful. Your structure should be simple and symmetric. Remember, if your structure is symmetric, then torsion can be eliminated from your structure, right? So shear wall must be placed symmetrically, remember. Right, and this is the response, and then you see here, this is the most important part. Here what is happening? You get the acceleration, right? You get the accelerations here, which is abruptly changing, right? Here you can see, which is changing, right? The peak acceleration, and the acceleration what you are getting in both the direction, not in the one direction. You see, we are shaking in one direction, but you get the acceleration in both the direction, right? That is generally, if your structure is unsymmetrical, then your structure is having the torsion, and then this is going to observe, right? The next is a pounding, right? Pounding means when two structures are close to each other, then what is going to happen? They will hit each other. They have an impact between them, right? So what is going to happen? Like this slab will hit this column, right? This slab will hit this column, and what is the result? The result is, I think you can see here, there is a collapse. You can see here, there is a collapse, right? This structure is collapsed. What is the solution then? The solution is you make your structure stronger than the adjacent structure. That is not the solution, right? We have to find the solution of this. Here you can see the top part, because of the impact, it collapses. You see, we have designed our structure for earthquake, but we have not designed for this impact force, additional impact force. And this pounding will come in picture during the earthquake only, because it comes in lateral direction. Earthquake shakes your building in lateral direction, and therefore this impact comes in picture. And you can see this, right? You can see this. This is the collapse, right? So we have a model without pounding of the slab with column, pounding of slab with slab, right? So here you can see, if we have these two structures and we put them on a shake table, then this slab will hit this column, right? So it is basically slab to column pounding. And here this is slab and this is slab. So here the slab will impact the slab. So it is the slab to slab pounding, right? So the solution is you have to provide a separation gap between them, right? So here we have another video where we perform the test. You can see here. Again, first I explain this. You can see the height of this model is high, so frequency is low, and height of this slab is less, right? So frequency is high. So both is having different frequencies, right? Now what is happening? Just look at this. When the same earthquake motion is applied, the slab is hitting the column. Slab is hitting the column. And even though if this column is designed properly for the earthquake force, this additional impact will cause the damage, right? So you have to avoid this pounding by separation gap. Remember, that is to be required. Right? You can see this is the impact, and a large sound is created. I tell you, if I show you the sound, then the sound is very. Right? So this pounding to be avoided. Pounding to be avoided. Now we talk about the pounding slab to slab. Again, problem of rotation is here. Here, both the slabs are at the same level, and we can see what is happening. Right? This pounding is having a larger impact, I tell you. So actually the impact, when the impact will come, the force will become double. That we understand in structural analysis, right? So it will hit with the double force when impact will come, as compared to the gradually applied force, right? So we have to avoid such kind of things in the real life. And this is the response we are getting, right? Through analyzer we get the response, and you see when the impact is going to take place, then this acceleration is also increased. And if this is very important here, the maximum force here comes out to be, this is the additional force you have, right? And we have not designed for this additional force, and then your structure may collapse, right? And you can see here when the impact comes, you have a larger acceleration. You can see these are the peaks. These are the peaks because of the impact, and larger acceleration will be observed, right? And it should not happen in real life, right? This is to be addressed properly. Okay, so here you can see these are the results, and again the maximum force, which is again additional force which is applied, which is for which your columns are not designed, so therefore damage or collapse is observed. So the solution is provide the gap. If you provide the gap, you have to design the gap in this way. The 0.4% drift is allowed as per the Indian code, right? And the gap should be 0.04 h into r, response factor. This is r. So this should be the gap you have to provide it. 0.02 h. That should be the gap for the ductile building having r is equal to 5 value, right? So proper estimate of the gap is required, and provide a separation gap. Then we talk about sometimes we came across the L-shaped building, C-shaped building, H-shaped buildings. Are they good, or they are okay, or they are not good, right? So we have to look at this part. Under normal, under dead load and live load, there is no earthquake, no wind, that is fine. Then these buildings performs better. We have such kind of configurations, right? You look at this. We have the C-shaped buildings, right? We have the L-shaped buildings, right? This is a L-shaped building we have, right? L-shaped buildings. It will be like this. We have again a C-shaped buildings, right? This is also a C-shaped building. This is L-shaped building. These all buildings are located in Ahmedabad, I am saying. And here you can see one ground plus 10-story building collapsed during Bhuj earthquake. And you can see this is a Sikhar building in Ahmedabad. It was a C-shaped building, and it was collapsed because of the geometry. This was one of the reasons, right? Why it was damaged? What is the reason? Why this was happened? That we have to discuss. These are the L-shaped buildings, right? So sometimes you see this is the classical example. Sometimes the architect is saying, okay, this is my front side, so you cannot put a shear wall on this side. They say that okay, stair or lift should be at the on the rear side. So here the lift is placed. Now lift is made up of the RC wall, so it is too stiff, and this is quite flexible. So what is going to happen? This flexible part will move more during earthquake, and stiff part will remain as it is, and then we observe the damage, right? So this torsion is going to come. The whole structure will undergo twisting. That's why I'm saying that we are not able to handle earthquake force, and if you add torsion in it, then you make your life miserable. So you have to avoid torsion as far as possible. You can see these are the failures observed. This is because of the shear building, it is collapsed. Here you can say this is a stiffer part, or this is a flexible part. Again, collapse is observed. You can see this collapse because it is a. Here also the front part was flexible, this part was flexible, and the shear wall is on the back side. So the front part collapsed, and this was happened. Right? So we have prepared a model. Now in this model, actually this is the one part, this is the another part. Both are separated, right? Both are different structures, but the connection is provided here. The connections are provided here, right? So if I connect it, it will become a C-shaped, L-shaped building, right? If I don't connect, it will remain normal structure, right? And these are the results we have. I'm not going to discuss the result, but I'm interested in the performance, right? If you look at the performance, look at this, right? When I connect it here, this both are connected, right? Generally, L-shaped buildings, we have a common structure element. So here it is connected, and now what is happening? Just look at the behavior. You can see instead of displacement, you have a rotation also, right? Rotation also. It means torsion is introduced in the system. And when torsion is introduced, your columns are excessively stressed. Just look at this. Yeah. So larger torsion will come, and this results into a collapse of the structure. So L-shaped buildings, C-shaped buildings are not performing well during earthquake. Remember, because of it generates the additional torsion in the system. Additional torsion in the system. Right? Look at this. Torsion is there? Yes. And because of torsion, what is happening? You can have the acceleration in all the directions, right? Then we have a liquefaction model. Liquefaction model. What is liquefaction? Liquefaction means when your structure is located on a sandy soil, this is going to happen. We are knowing that soil possesses two things: cohesion and friction. Cohesion and friction, right? Now, the strength of soil comes from C and phi. Now, when your structure is located on cohesion-less soil, cohesion-less means C is 0. So the strength of soil depends on only friction, right? Now, if I'm talking about a sandy soil is a cohesion-less soil, right? Now, if sandy soil is there, and if the water table is high, during shaking, what is happen? Water will come out. When the water will come out, it will fill the space between the soil particles, sand, right? So if the space between the sand particle is filled up with the water, then there is no friction. If there is no friction, then now there is no cohesion, there is no friction. So your sandy soil with the high water table behaves like a liquid. And if your structure is located on such kind of soil, structure may tilt, right? This is going to happen. This is not soil liquefaction. So what is the soil liquefaction? The soil is losing all its shear strength, right? All its shear strength. Okay. So therefore, your soil will not going to support your structure. Simple example. Suppose if you want to walk on water, right? What is going to happen? Are you able to walk on water? No. What is the reason? Because the water don't have the shear strength, right? So you will basically sink in that. Now, if your structure is located on a sandy soil with a high water table, then the sandy soil is not going to support. Sandy soil is going to behave like a liquid, so it is not going to support your structure, right? So basically, we have prepared a model with the isolated footing, raft foundation, pile foundation. 1 minute. So I think videos are not right now here. I'll show you maybe separately. And the last one is important part is as far as the model is concerned is the reinforcement detailing. right? In earthquake, we are going for the ductile detailing, right? Ductile detailing. Ductile detailing is very important for us because we highly rely on ductility. And suppose if you design your structure for dead load and live load, you can follow IS 456, right? But suppose if you want to design your structure for earthquake, you have to introduce ductility in your structure. And you can see here, these are the failures, right? This falling of the concrete because of the strong shaking. Here, the failure of shear failure of the beam is observed. Here you can see shear failure of the beams is observed because of the poor detailing, right? You can see the detailing. Now here you can see, we are knowing that plastic hinges are formed at the top and bottom of the column during earthquake because these are the region where the highest maximum moment and shear is going to come. So we can see the second kind of failures. You can see here. This is failing, right? You can see this is failing, right? Because of poor detailing, poor reinforcement detailing. Here you can see the spacing of the shear stirrup is quite more, means quite high, right? Here you can see the reinforcement detailing. Shear stirrup is not closely spaced as per the IS 1893, right? So you have to be very careful. Here you can see bulging is taking place, right? Here you can see the improper detailing you have, right? Because of inadequate shear stirrups, right? Here you can see here is inadequate shear stirrups. We know the maximum moment is at top and bottom, so you have to go for the closed stirrups at top and bottom. That is to be required, right? And otherwise failure will be observed. Here you can see these are the various pictures you have, right? So what you need? You need a closed stirrups and with a 135-degree band that is to be required, which are placed in opposite direction in subsequent rings, right? So closed stirrups required near the joint, right? So here you can see if it is closed. This is a column. In column, closed space stirrups, space stirrups here, and the lapping is allowed. Lapping of the longitudinal bar is allowed in this particular portion, but you can lap only 50% bar at one point, right? So closed stirrups you have to provide when the lapping is there, right? And here this is the extended region. This is the foundation, and then you have to go for the spatial confining reinforcement here. Otherwise, your structure may fail here. And therefore, one model is prepared to show the ductile detailing. You can see here. Now he is Professor S.K. Jain, who is the director of IIT Gandhinagar. He is looking at this model. Here you have a closed stirrups. Here at the bottom you have closed stirrups, and in the middle you are providing a lapping. 50% bar are lapped at one place. 50% bar is lapped at the other place. Now he is a Japanese engineer, right? This is demonstrated during the international conference at Gandhinagar, right? You can see this. These are the well detailed detailing. So this model will show you how you have to carry out the ductile detailing, right? So these are the models we have. So finally, come to the conclusion that the behavior of the simple structural configuration can be understood easily by these experiments. The experiments always give you the insight, because you see, when I was studying, when my professors was telling me that your structure is going to experience torsion if it's unsymmetrical. You see, if professor is saying, then we have to believe in that. But we are not able to visualize. But when I see that, okay, if torsion is there and when I apply the shaking, then it shakes. So and torsion is introduced. So it always comes in my mind that, okay, that this is going to happen, right? That it is very easy to understand that part. So experiments will give you the enough insight, right? The result of the experiments are verified by generating the model in software. Basically, don't rely on only experiments or only your software model. You have to correlate, right? You have to verify these things, right? And then actual boundary condition can be derived by comparing the experimental and analytical values, right? So there are many references used, and I think my guide was Dr. H.S. Patil, and then all have helped me a lot. Professor Murthy, Professor Durgesh Rai, they have frequently visited our lab, and they have given a very good input to us to make our lab strong. Even our chief minister at that moment has reviewed the whole project, and I think we have prepared this model with the help of Gujarat State Disaster Management Authority. So it was a wonderful experience. We have this is a Professor Murthy, and this is Professor Marshall from the Peru. He has also given a good insight. He has visited the lab and given good input how to make your lab more versatile. Right now, we are working on vernacular housing, traditional housing systems in our laboratory. We are developing a comprehensive shake table, maybe of size of 10 feet by 10 feet, and we are going to take half-scale model of that. So it is under process. You see Svetlana Brezev and the Japanese experts. They have also reviewed this. Here we are testing the traditional housing. Here's Professor Marshall and Professor Svetlana. They are well-known earthquake engineers. Marjorie Green, right? So basically, our experience was that we don't have a good earthquake lab facility. Therefore, we are not able to understand the earthquake behavior. And the purpose behind this development of this laboratory was to understand the behavior of structures through the visuals. So that was the basic purpose, and students have, I think, have given a wonderful feedback that it is very difficult for them to understand the behavior, right? So here I stop. If you have any question, you can ask, but always believe that never give up in your life, right? That should be the spirit you must have all the time. So if you have any question, you can ask, please. Thank you.
Thank you very much, sir, for the wonderful lecture. Actually, we all were feeling that we are in the lab only.
Yeah. Basically, these visuals always give you a better understanding. Yeah.
True, sir.
Yeah.
Participants, you can unmute yourself, and also you can keep your camera also on mode. You can ask questions. Sir, I am having 2 questions.
Yes.
Sir, we are also having that shake table. That we have to give input in terms of frequency and displacement. So how we will get that G value, sir?
Basically, for the G value, you need accelerometers. So you need a sensor. So when you put accelerometer there, right? We have placed accelerometer on the shake table, and first slab, second slab, third slab. So you can record that through data acquisition system. So you need a data acquisition system which will capture the accelerations and other parameter displacement, everything, frequency, everything you can get from this system. Yeah.
Okay, sir. Thank you, sir. Yeah. Sir, one more question is there, sir. Sir, actually, generally there are 2 types of buildings are usually made. One, in the lifts they are keeping the first story, second story, third story up to the floor where the lift is going as a core wall, shear wall.
Yes.
Concrete shear wall. But at some places they kept only basement portion as reinforcement. RCC remaining portion they are making brick. They are keeping brick masonry.
Yeah.
So what is the difference between these 2 structures?
You see, when we go for the always in case of earthquake resistant design, the shear wall performs important role, and shear walls attracts larger earthquake forces, right? So if the good shear wall is provided, then most of the earthquake force taken by the shear wall, and your other columns will become relaxed during that time, right? So you see, we have to construct a lift well because we have to provide a lift. So we require a wall. So if you provide a shear wall there, means concrete wall, if you provide, then it behaves as a shear wall. And during earthquake, it will take a load of columns, and it will help the columns to take that load. So instead of going for masonry shear wall, you have to go for a concrete shear wall, and it will be good during the earthquake, and it attracts larger earthquake force, and your building perform better as compared to masonry shear wall.
Thank you, sir.
Yeah.
Participants, you can also ask questions. Or you can mail us. We will send it to sir, and then we will revert back you once we get the response from sir.
Sure.
So, sir, now we are moving towards valedictory and feedback session.
Right, sir. So thank you very much, and I think the session you might have came across good information, and I think it will be useful to you. Any moment if you want any help or anything, we have a good laboratory and we try to help you in any way. So I think in future, if you have any query, you can contact us, and we will try to help you in the best possible way. Thank you. Thank you.
Thank you very much, sir, for motivating us.
You are putting a lot of effort, and I think it will be very good for the students, I tell you.
And sir, we need your support in the near future also, sir.
No, sure, sir, sure. So should I leave now, or?
Sir, if you want, you can say a few words to our participants.
I already told that, you see, as a civil engineer, people are putting a lot of faith. I had given example that we are not like other industries, and basically civil engineers, we are designing, we are executing our structures with the theoretical knowledge and something which is the data which is available regarding the materials, and then we are executing such 100-story structures. So they have a lot of faith in us, and we have to prove that faith, right? So for that, I think a lot of commitment we require, and during the disasters, we feel that this faith was little bit trembled, right? So this should not happen, and in India, a lot of opportunity is there, and in India, I think India will become developed country maybe within 10-20 years, and a lot of reforms will come to construction industry, like what Japan has done, what America has done, or New Zealand has done. The same thing, this stage will come in India also, where you can give your input and you work like anything. You see, when you find that there are less number of structures in India with structural control systems, means, you see, as an engineer, you have to be excited. You have to feel that, okay, less number means there are a lot of opportunity we can start this in India, right? So this you can do. So you can make wonders, I tell you. You can initiate certain things in India. So take it as an opportunity, right? Don't feel that India don't have such kind of advanced structural systems and we are not implementing that. But this will give you the opportunity to prove yourself. Go with it, and I think you can do wonders, right? That's all. Thank you.
Thank you very much, sir.
Yeah. Okay, thank you. Should I leave?
Okay, sir. Yes, sir.
Okay,
yes, sir.
thank you.
Thanks a lot, sir.
Yeah.